Okay, so we want to talk about MOSFETs now. So a MOSFET is a different type of transistor, similar to, but a little bit different than the BJT. So first of all, here is the MOSFET page in Wikipedia that shows all of this. But it's interesting that in Wikipedia, it said it's the basic building block of modern electronics, and there is an estimated 13 sextillion 1.3 times 10 to the 22nd MOSFETs that have been manufactured between 1960 and 2018. So that is a lot of MOSFETs. So there's a lot more MOSFETs than BJTs that are made. So the traditional metal oxide semiconductor, which is your MOS, right? That's the MOS of the MOSFET structure, is obtained by growing a layer of silicon dioxide on top of a silicon substrate. Okay, so what in the heck does all that mean? Okay, so let's go look at what a MOSFET looks like. So here is a MOSFET. So it has an N region, an N region, and then it's grown with a P region in between. So it looks a lot like an NPN region, except for in this case, the connection to that middle region is insulated. So it's insulated by an oxide. So it has a complete insulator separated between the two, where with the BJT, this insulator was out and we made contact to that middle P region. Okay, so we need to look at operating regimes on how this works. So let's go here and look. Okay, so here is your basic MOSFET. So I have an N region, a P region, and an N region. So this is my NPN region. It also connects over to the substrate over here. We don't really care about that. So we're looking right here. So the NPN creates a depletion region, just like we had with the BJT. And then the PN region creates a depletion region over here. So we have two depletion regions, looks like the two back-to-back diodes, just like we had with the BJT. But now I can't make direct connection right here. I only have a capacitor. So what this ends up doing is, if I move over to this figure here, when I put a voltage across here, it's taking and pulling these excess carriers up into this region right here. So what it basically does is creates a channel. So now I create a channel that lets currents flow through here through this channel. The bigger the voltage is, the bigger the channel, the lower the resistance. So if I make a high voltage here, I can create a large channel, and then I can affect how easy it is to flow current from the drain to the source. So you see that this gate region is still my control region. So this is kind of like my base was before to do the control. Okay, so now if I increase this voltage, but eventually when I apply voltages across here between my drain and my source, it kind of changes it, and I get what's called this pinch-off region. So when I get this pinch-off region right here, where this kind of does, then this is going to be like active. So now what's going to end up happening is that the current flow from my drain to my source, it has kind of like this fixed channel. I'm going to get a fixed current through here. So as this voltage changes, so you can kind of see right here, if my drain to source is greater than some value, then my current's kind of fixed. So this region right here is basically the same as active. So this region right here, which is called the ohmic or triode region, is similar to my saturation. And this region here, which is called saturation, is actually my active region. So that gets a little confusing. So we're going to call this one active and this one triode. Let's look at these currents in a little bit more detail. So the cutoff one is pretty straightforward, that there's some threshold voltage that when I'm under that, then it's just zero current. The other two, we look at these parameters in the front. So let's start with the mu sub n. So the mu sub n is called electron mobility, and it is basically how fast can an electron move in a given electric field. So when we have an applied electric field, we get this electron mobility, and that determines how fast the electrons are moving. So for silicon, let's see, so for silicon, crystalline silicon, it's just a number right here, 1400. Here's the whole mobility, and like we said before, electrons are just electrons are lighter than holes, or holes are heavier. So we see that these are just some parameters that come from silicon. Not much we can do. If we want to change that, we have to change the materials. Okay, so then we have the C aux and the W and the L, and those are all basically parameters of the MOSFET. So let's go look. Here is a basic MOSFET. And so what we can see here is that we basically have this insulator right here, source, drain, and gate. So between these two materials and the gate, there's an insulator. So there's some oxide that separates the two, and we basically have created a capacitor. So the C aux is the capacitance per unit length. So that's going to be primarily dependent on the material and the thickness of this oxide layer. The length is basically the separation between the drain and the source, and the width is how long we make this transistor. So typically when you're fabricating MOSFETs, this length is held constant for all the transistors, and then we can just kind of make this width as long as we want to fix those parameters. So typically, so we can kind of see, typically what we do is we're going to come in here, and in LTSpice, it calls this whole parameter K sub P. And you can kind of see that in the other mode, we have the same term. That's just the K sub P. It's just in one case, it's K sub P, and the other, it's K sub P over 2. And so you can see that we get to adjust the Kp by playing around with the oxide and the size of the transistor. So as the transistor gets bigger or smaller and this oxide changes, we can change the Kp, which is going to change your current characteristics. And then to see over here, this tells you the parameters on when I'm in triode versus when I'm in active. And you can see here, this is when my current is small. I mean, when my applied voltage is small. So when my applied voltage is smaller than this parameter, I'm in triode. When my voltage is larger, then I'm in active. Okay, so now that we understand these, let's go and look at LTSpice and look at these plots. So we're going to look at the gate to source first. Okay, so what we're going to be doing is, here is our BJT that we had before. And if I'm putting a voltage onto the base emitter, which is my control. So if I look right here as the current as a function of V of my base, you see I end up getting this exponential type relationship. I end up getting some RS, and so it ends up going linear when I get to this point. But we see that this has, here's my 0.7 volt turn on voltage. Okay, so now let's look at the MOSFET. So the MOSFET, let's change this to V of the gate. And you see it looks kind of similar. I got very low current, but it doesn't turn on at 0.7. It turns on at some threshold point. So if I look at this MOSFET here that I'm using, here is my threshold voltage right here. So we have the V threshold is 1.6 volts. So when I get to 1.6 volts, then it starts to conduct up. But you see that that has a similar shape to this one. You know, this one tends to be a little steeper, but you still see I have a turn on voltage and then it goes up. Okay. And the higher my gate to source is, the higher my base to emitter, the more current I get through. Okay, so now we're going to look at my drain to source voltage. So now you see I'm putting in a base emitter voltage and I'm sweeping this. So let's look at this one first. We're going to look at the current as a function of V of C. Okay, so let's kind of review our BJTs. This region right here has a very small dependence on the collector to emitter voltage. So as my collector to emitter voltage doesn't affect my current, it's fairly flat. I have a little bit of slope. That's my early voltage that I had before. And then this region right here is when I hit saturation. So then when I hit that 0.2 volts, you see that my current just drops off because I went into saturation. Okay, now let's go over here and look at our MOSFET. Change this to D for my drain. Okay, and it looks fairly similar. So here is my active regime where I have a small slope. I still have the early voltage, but rather than calling it early voltage, they call it channel length modulation. So instead of using VA, they use 1 over VA, which is called lambda. And then this regime right here is my triode. Okay, and you can kind of see it's a little bit wider than it was for the BJT. So this region right here is a little bit wider, but you see that these shapes look very similar. So most of the stuff that I did with BJTs, I can do with